Welcome. In this video I'll go through the delta W calculation of stability for pinches, so the theta pinch and the Z pinch. And this is a bit more mathematical, so a bit more rigorous in some ways, but hopefully if you've seen previous videos you might have some understanding of what these modes look like. And now we're going to try and calculate stability a bit more thoroughly by using the delta W equation. That's the energy principle, just finding modes where the potential energy drops if you perturb the plasma. And so this gives us a way of working out a condition for stability of the plasma. So first just write out the delta W equation. And this is the sum of three components. There's the plasma component, plus the surface component, plus the vacuum component. And we write down here, so delta W plasma is what we've concentrated on most. The surface term we wrote down originally, so delta W S is an integral over the whole surface. And this we can write in a few different ways. First, we just write this as this is just delta. This part here is just delta P. And we can actually group this together and write this whole thing as an integral over the surface. So that this is like a loop integral, so a closed surface around the plasma, and it's the jump. I'm going to use this to mean the jump in the gradient of the total pressure, so the magnetic field plus the plasma pressure. And it's the displacement dotted with the surface normal vector. Now this total pressure, this is obviously constant across the plasma, but the gradient doesn't have to be. And so in general the gradient can have a jump, and so we might have if this is like the radius out here, and this is the total pressure, so P plus B squared over 2 mu naught. They might have some kind of jump down here, and then for example a kind of cusp. And at this point here we might have a surface current, which is holding back this jump or change in pressure gradient, and so this here is a jump in gradient. So the point is that mainly that you can make this term go to zero if the solution is sufficiently smooth. So if there's a smooth solution with no jump in gradient, then this term disappears. And then lastly you have the vacuum component, which is always stabilizing, and this is just the total energy put into the magnetic field. So it's delta B squared, mu naught. That's always bigger than zero and always stabilizing. Okay, so the main things here, we'll just say that we can have modes driven by surface terms, but for analysis here we'll assume this term is going to zero, because the plasma is sufficiently smooth, and then we'll look at what drives these stabilities here and the terms on the top that suppress or stabilize the plasma. And so first we look at the theta pinch, and this is a geometry where we have a cylindrical plasma like this, and we have a magnetic field running down the axis, so B is just straight through here, and they have a current which is running around the outside or inside the plasma, so current is running around here. This is J, and this is the net force is inwards, and this is just the diamagnetic current. And then if you want to compress the plasma, you increase the magnetic field and cause inward compression. But in this case, the current and the magnetic field are at right angles, so J is basically just the diamagnetic current, so it's just B cross grad P over B squared, with a charge in there, and then so J is like this, and that means that the current is perpendicular to the magnetic field, so J is perpendicular to B, and so the parallel current equals zero. So there's no net current. So I'll put the charge here, Q in. Okay, So then there's no parallel currents, there's no kink drive. So B field is straight, so there's no curvature. And together this means that there's no drive for instability, because both these terms which can drive instabilities, the kink term here and the curvature term, are both 0. And so this configuration is stable. The more difficult, more interesting case is the Z pinch. So if we go to a Z pinch where we have the current running down the middle. So here there's also a cylindrical equilibrium. We have a cylinder with again now current down the middle. So current is here and magnetic field around the outside. So B is like this, and now we have a curvature we've done before. So kappa is inwards, as is grad P, but because the current and the magnetic fields are at right angles, so J is also perpendicular to the magnetic field. So therefore J parallel should be B. So J parallel is 0. So here there are no kink modes, but there are pressure-driven modes. So we have a curvature, we have grad P, which is also inwards, and so the terms which are important are the stabilizing terms, and so these terms at the top, and this term here, involving the pressure gradient and the curvature. So this term has gone to 0, and this term we're ignoring, and the vacuum we assume is always stabilizing, so whatever we find is always an upper estimate, or a worst case. So here we'll start analyzing this. So we want to look for pressure-driven instabilities, and the first thing we can do is try to work out what the perturbation looks like. And one of the constraints we can use is that the plasma should be incompressible. And if you saw a previous video, showed this can usually happen, except where B dot grad is 0. This is singular surfaces. So if you have an instability which is constant along B, so a displacement, for example, then we can't make this 0. But if we have a displacement which is, say, twisting the magnetic field, then we can make this the case. So what we're going to look for are modes where we have, so the plasma is being displaced. So we'll start with a cylinder, and it's being displaced so that it's twisting. So the whole plasma is kind of twisting into a helix. So this is the displacement, and it have some wavelength along here. And we'll use the so K, so we'll see 2 pi over some kind of wavelength. And then here we have some kind of mode number. So we're looking for Fourier modes in this direction. So here this would be m equals 1, because this side, here we have displaced this that way, and here we displaced this that way. So the displacement has a mode number m. So m equals 1 is this case. M equals 2, for example, would be if we had a plasma cross-section and then we distorted it so that it ends up with kind of a plasma twisting so that part of it's gone in. So we started with a circle. So here we've got parts have gone out and these have gone in. We might have this whole thing kind of twisting as well. Here we have something which is kind of twisted. So it has a wavelength in this direction, so it has some kind of twist. We have the field going inwards again, and outwards here, and that would be an m equals 2. So m equals 1 is kind of special in that it's not changing the shape here of the cross section; it's just moving the whole plasma. Whereas m equals 2 is now distorting and twisting squashing the plasma and moving it like this. So we're looking for Fourier modes which have a mode number m in the poloidal direction and a wavelength with a k in the z direction, so along here. So if this direction here is z, this angle around here is theta, so theta is around this angle. And so we're looking for perturbations, so displacements of the plasma, which have some kind of dependence on r, theta and z, and also on time, and this will be some kind of combination of Fourier modes. So we have some kind of Fourier mode here, which depends on r and time, and then it has an e to the I, we have m theta and an I k z. So m is here the poloidal mode number, some kind of integer, whereas k is the basic one of the wavelength. So now we can write down the equation for divergence in cylindrical coordinates. And so we just write down the divergence of displacement. So here we have split psi up into its different components. So psi in the radial direction in the poloidal, so the angle direction, and psi in the z direction. And then we can rearrange this and just say this whole thing must be equal to 0. We can now put this Fourier mode into this equation. Most of the terms will cancel out, so this factor of psi hat will disappear, will just cancel out. What we'll end up with is, so the Fourier, using the fact that this is a Fourier mode in theta and in z, the d by d theta just brings down a factor of im here, and the d by dz just brings down a factor of ik, which is this factor here. And so we then just rearrange this whole equation. And what we want to find is an equation for the parallel displacement. And because the field lines are in the theta direction, what we want is psi theta, which is just the parallel component of the displacement. And so if m is not equal to 0, then we can do this. So remember, m equals 0 is the sausage instability where the whole plasma is being compressed, and in that case the plasma will be compressed because there's no way for it to go. Here we're just looking at cases like m equals 1, m equals 2, where the plasma can have a parallel flow. And so if m is not 0, we can write down, and so then we can just choose this psi parallel, and if we choose it to be this, then we minimize and we set this divergence to 0. So then we can start trying to look at the other terms in the equation and minimize, work out what they are. So we've eliminated this term here. So I'll write these down here. So this was eliminated because there's no parallel current. We've eliminated this because it's incompressible. And so now we need to work out what these terms are. So let's work out what the perpendicular component of the perturbed magnetic field, so delta B perp. So we can work out that, so delta B is the curl of the displacement across the equilibrium magnetic field. And this we can expand out as a vector identity, and this is, so we have a divergence of B, obviously is 0, then we have a B times a divergence of xi, which you just decided is also equal to 0, and then we have various components, so we have a B dot grad xi minus a xi dot grad B. So these two terms are both 0. And we just got these two components, and they we can work out. So first B dot grad psi. So B is in the poloidal direction, and so this is the gradient in the poloidal direction of xi. So this is B poloidal times d by d theta. So it's in the theta direction. 1 over r, because this just from units, well, this is derivative with respect to a length. This is r times theta is the poloidal length, so this together is b dot grad, and then here we're taking derivative of xi. And then the other component is that if we have xi dot grad b, so b only has a poloidal component, and it's constant in z and theta. And so this whole thing just becomes, so it's only varying in r, and so this is just psi r times db theta by dr. That's in the theta direction. So with these two components, we just put this into this equation here, and write down that delta b. So this b dot grad we write out as b theta over r d by d theta. Then we write out the various components of psi. And then with the second term as well, so then we have a minus psi r db theta by dr in the theta direction. So this is the total b perturbation. What we want is the perpendicular component, so delta b perpendicular, and the perpendicular part is this with all the components in theta removed. And so this part here with in theta is a parallel displacement, as is this. And so the only parts which are parallel, which are perpendicular displacements, are this one and that one. And so we just end up with this is, and of course if we're looking for Fourier modes, this d by d theta just becomes an im, and so we just write this whole thing as just im b theta over r, and then you have a psi r hat now because it's the Fourier components, r hat the unit vector, psi z, and then a z unit vector. Because this is enough to get the components of delta p perp for the field line bending term. If we go to the other term in the equation here, so here we have a term, this term here in the middle, so we have a magnetic compression term. So a divergence of psi perpendicular plus psi perp dot kappa. So you can calculate what this is. So psi perpendicular is just the r and the z components. So you just write down the r and z components of divergence of psi. So this part here. So this is, so that's the divergence of psi perpendicular. This part we'll get just from kappa. This kappa is just 1 over the minor radius, the unit vector in the r direction. It's minus because it's inwards in r, and so the whole term just becomes a minus 2 psi r over r. And now these two components here, so this part here and this part here, so these two can be combined. These two combine together into term r d by dr psi r over r. So you can multiply this out and convince yourself that this does give you that. And then we have the second term here which comes down, so plus ik psi z. And then finally we have the drive term. So we have a term with this factor, so psi dot grad p naught, and we have a kappa dot psi, which would be psi perp star. Okay, so this time there's a factor of minus 2 in the front, but we'll just deal with this for now. So this, again, we just use this expression for kappa, and this, of course, just gives us a psi r. P is also only varying in r, and so these two components just give us a psi r squared. So this just gives us minus mod psi r squared, so one's a complex conjugate of the other, and this is over r from the kappa, and then times dp naught by dr. Okay, so now we can put these components together, and the plasma components, so dwp, we can just write as, so this first term is the field line bending term, so this is delta b mod delta b perp squared over mu naught, and so we had an I with an m b theta over r, and 1 over mu naught comes from here, and then this is the perpendicular magnetic field perturbation. Then we're going to add on the parts from the magnetic compression, so this part here, and then finally we have the term from the pressure and curvature drive, just this one here, So there's a factor of -2 at the front, and so this whole thing just becomes a +2 here psi r over r, and then a dp naught by dr. So those are the three components that are not zero in this case. And then the next step is to try and eliminate at least one of these displacements. So we have psi r in here, and we also have a psi z. So we have psi z here and psi z here. And the way to eliminate this is to try and combine them into a single expression, so completing the squares. And what you end up with, if I write out here, is an equation where you have delta w. And you can see where this comes from. If you look at this term here, so we have a psi z here is the only term now which contains this z component of the displacement. So you've got m squared over r squared and a k squared. So this just come from this. So m squared over r squared has come from this component here, and the k squared has come from multiplying this out. And so if you take this term here, multiply it out, you'll end up with most of the terms I've just shown you, and then you end up with this extra bit here. And so by working backwards from here, you can show that you get the previous result. And now there's a few things we can do here. So firstly, this is now the only place where psi z only appearance. And because this whole term is stabilizing, an instability will try and minimize delta wp. And so this term is all stabilizing. But we can make it 0 if we choose psi z correctly. So if we choose psi z to be this, then these two will cancel out and this whole thing will go to 0. So we can basically make this whole part, this part here, cancel out. If we choose psi z correctly. And then the next part to notice is that this term here, if you make k large, so here k appears underneath here and doesn't appear anywhere in here, and so this term, so for k large, this stabilizing term also disappears, and so at large k is the most unstable. So k large is the most unstable. Because if k is large, then this stabilizing term goes to 0, and so what's left is this term here. And so this term is multiplying psi r, so psi r squared is positive, and so if this is negative, then the whole thing can be unstable. And so we need, for stability, we need m squared, we need this term here to be bigger than 0. And of course dp by dr is negative. And so this gives a limit on the pressure, beyond which, if the pressure gradient is too large, then this will be violated and you'll get an instability. And this was an instability or threshold derived by Kadomtsev. I think it was 1966 in this case. So that's an example of how the delta W equation is used for calculating stability or deriving a condition for stability. And in this case, it's this one for a Z pinch. At least when m is not 0. Remember, there's another condition when m equals 0. We get the sausage instability. And in that case, plasma compression starts to become important. But this is the general procedure. So we start by looking at which terms in the equations are 0, so cancelling out as many as possible. And then usually start by trying to minimize this component, so minimizing the compressibility, because that's where psi parallel appears. And then try to derive all the other expressions, and then simplify them and factor them out. And often, in this case, we also try and remove components. So here we had psi r's and psi z's, and then we try and remove psi z. To end up with a single equation for psi r. And more general geometries are more difficult to calculate, but all have a similar kind of procedure to doing them.